Hello student, welcome to the Wave Optics course. Today we have lecture number 47, and in today's lecture we are going to discuss about the diffraction phenomena for an arbitrary aperture and how it happens in Fresnel's case. So today we have lecture number 47. And today we are going to discuss that how Fresnel's diffraction happens for an arbitrary aperture. So before doing the specific case, we need to do this to understand few aspects. So let us do that. So suppose we have a system where this is a arbitrary aperture and this is a coordinate system. This is xy coordinate system where we have an aperture which is placed like this, and then we have a screen here. This is the screen where the pattern will going to form. And also there is a coordinate here which is big xy. So if I have, so here z is 0, here it is some z point. So the coordinate of any point P over the aperture is simply over the screen is simply x, y and z. Now I have a point here, x and y coordinate, a small section here, and if I join this point to P, this is say R prime, and from the center to the point P, this is R. This is the total picture we have. Now if a plane wave that is incident normally on this diffractive aperture which is shown here, we say it is A, for example, this aperture is A. So when the plane wave is falling here, then what happened? The light will be going to diffract here, and the field at point P, due to the small area dx dy, this is a small area over this aperture, I write it dx dy, it should be dep this is the field due to this small area dx dy at the point P is, we did it earlier, it should be E0 divided by R e to the power of I kr and dx dy, d small x dy, where our R is simply x minus small x square plus so and whole to the power half. That should be the value of R if the coordinate of this point is x, y and z equal to 0. Now the total field, if I want to calculate at P, will be simply the total field is EP, that will be some proportionality constant and then I need to integrate. Where alpha is a constant so essentially we need to over this aperture, this integration over this aperture, full aperture area A. So the essential thing is to execute this integral for this particular problem, but before that we can try to find out what should be the alpha with certain boundary condition, and that is an interesting kind of approach. We are going to use these things for other aperture, other structure, regular aperture. This is an arbitrary aperture, but regular shape aperture like specific aperture like edge of one sharp edge, then a circular aperture, etc. But before that it is interesting to find this proportionality constant alpha. So now in this class we are going to find out how to get this alpha. So determination of alpha. So we have EP equal to this constant that we had, right? Now note that in absence of aperture A, suppose there is no aperture at all, the plane wave simply moves through this system and then EP will be simply a plane wave, and EP can be written as E naught e to the power of I k r. This is a plane wave, and we can have this case when there is no aperture. That is, I just simply remove this aperture that is placed in the xyz equal to 0 plane. It is removed. That means I gradually increase the area of this aperture. This area tends to infinity. That is the condition I put here. So that means if that is the case, then we can simply write from here that alpha integration, I change this area, whatever the area, from minus infinity to plus infinity. That means there is no aperture at all physically. Then this integration will be minus infinity to infinity, minus infinity to infinity. Please note that this is alpha and this is infinity, it looks same. Then we have E naught divided by r e to the power of I k r. Then we have dx dy, and based on that condition I can say that this value, the left hand side, should be equal to simply E naught e to the power of I k r, because at the end of the day what we have is not k r, it is k z, because along the z direction it is essentially along the z direction the plane wave is moving. So that is the boundary condition we have, and from this condition, whatever the condition that is written here, we can calculate the value of alpha. Exploiting this expression, this condition or this equation, I can calculate alpha. So r I can write, let us write r here. If you remember, it was big X minus x whole square plus big Y minus y whole square plus z square. So if I take z common, then it should be z 1 plus big X minus x square divided by z square plus whole to the power half. Now this is much, considering x minus x divided by z and y minus y divided by z is much less than 1. So this is the difference, x minus x is the difference between 2 points, and z is the distance between, so if I go back to this figure, x minus, this is the difference between this coordinate and whatever the coordinate we have. So for all the points here, this value x minus x or y minus y, that should be very less than compared to the z. If I try to get it in the far away, then z is much bigger than this. So if I consider this condition, then we can have then we can have, maybe you can go, then we can have e to the power of I k r divided by r is nearly equal to e to the power of I k z divided by z into, so 1 by r term I just simply replace by z with that condition, but the rest of the term I keep it in exponential. Plus this. So what we did here, if I go back, what we did here, that then r will be equivalent to, under this condition, r, let me write it here, is nearly equal to z, and then I put this value as 1 plus x minus xs square divided by 2 of z square plus y minus y square divided by 2 of z square. So I just expand this, considering this condition that x minus x divided by z and y minus y divided by z is much less than 1, and then I expand. So this half term will come here as 1 by 2, 1 by 2. So that should be my r. Then in the next line, e to the power I k r, I just replace the value of the r. In the exponential, I kept this x minus x, but in the denominator, for the simplicity, I simply replace r as a z. So this value is essentially e to the power of I k z divided by z. Then we have, if I expand this into e to the power of, this is not x, it looks like x, so let me, so then e to the power of I k by 2 z, and I have x square y square term, so I have big x square plus big y square term. I wrote it, and then we have small x square and small xy, small x big and big x y term that is there. So I write the rest of the term like I k 2 z, then I have small x square minus 2 small x big X, that is one term, and also I have e to the power of I k divided by 2z this. So after that I put this condition to here, this integral, and we can write it alpha, then e to the power I k z divided by z, this term should come out, and also e to the power of I k by 2z, big X big Y term should come out, because this is nothing to do with in the integral. Integration is over small x small y, and then we have integration minus infinity to infinity one term, which is e to the power of I this is small x square minus k by z small x. This is one term in the integration with dx, and other similar looking term over dy, and it should be e to the power of I k by 2z y square minus I k by z small y big Y integral small y. The calculation looks big, but it is very straightforward, and at the end of the day we will find the value of alpha, that is the left hand side, and that should be equal to something in the right hand side, and that value, if I put here, look to this this equation, the right hand side, it should be e naught e to the power I k z, that is in the right hand side. So that thing is equal to, so if I go back, I integrate this entire thing, and on the right hand side I get, so e naught essentially will cancel out. So okay, we will come to this later. Now let us execute this integral first, then we will come to this. So I would like to note here one very standard integral, that is a very useful integral, and that is this, minus infinity to infinity e to the power of minus alpha t square plus beta t dt. That integral is equal to root over of, this is a very famous integral, and we are going to use this several times, e to the power of by 4 alpha, that is the result of this integral. This is a very famous integral. I suggest that the student should note it, and if I exploit this integral here in this, so you can see this is exactly the same form. Alpha here is I k divided by 2z, and beta here is I k z x. So if I exploit this integral here, then this integral x square minus I k by z x x dx d small x rather, that value if I put alpha and beta in that particular form, it should be simply root over of pi by alpha. Alpha is this quantity. So, I have pi divided by k, and then we have 2, and then this, there is a minus sign here, and if I absorb this minus sign, it should be 2 and then z and then I. That should be the value. Then e to the power of beta is this value. So, I can have e to the power of minus I k, then I have big x square divided by 2 of z, because this value is beta square divided by 4 alpha, and if I execute this beta square divided by 4 alpha, it will come like this. So, let me do that. Mind it, this alpha I am trying to find out at here, this is the general notation I am using, alpha and beta. This alpha is nothing to do with this alpha. So, please note that. So, here how I get this, I can quickly see what is the beta square. Beta square is minus of k square divided by z square and big X square. That was my beta square into beta square, and then divided by 4. So, 4 by alpha, alpha was this. So, it is divided by 4 into k divided by 2 of zi. So, this 2 will cancel out with 4, we have 2, 1 k will cancel out, and it should be 1 z is also going to cancel out. So, we have k multiplied by x square divided by so this z cancel out, there will be I here. So, this quantity we are going to get. So, essentially what we have is this, that alpha e to the power of I k z divided by z e to the power of I k divided by 2z x square plus y square, that value multiplied by e to the power of whatever we had here. I need to put here, we have this quantity and e to the power I k x square divided by 2z. So, for y also we have this term. So, if I put these two terms together, we will get a very interesting looking term, and that is minus of I k of k divided by 2z big x square plus y square, exactly the same term that we had here, but with a negative sign. So, this will cancel out, and then multiplication of 2 pi divided by k z I, that we can get from the first term. It was root over of this thing. So, for x and for y, this same term will come, pi divided by k 2zi. So, this root over will no longer be there, because two same term will come from x and y integral, and that is equal to, this value is equal to, okay, we have alpha here, alpha multiplied by this. So, that is equal to E naught e to the power of I k z. So, you note that this term will simply cancel out, e to the power I k z will cancel out, E naught will also cancel out, because here in this equation this E naught and this E naught was there. So, essentially this is E naught here. So, what I get is alpha equal to, very interesting result, alpha equal to minus of this term will go down. So, alpha is equal to minus of k of I divided by 2 pi. K is 2 pi divided by lambda. So, this also be written as minus of I by lambda. So, this is a very interesting expression we have. We managed to get with the boundary condition what alpha is. So, next time when we calculate for a regular structure, maybe in the next class we will do that, instead of writing this field, so that means my EP, the total field will be, in the previous case we wrote that this is this integral of E naught divided by r e to the power of I k r, and over the entire aperture area, that was the form. And after doing a bit lengthy calculation, we find that this alpha is essentially minus of I k divided by 2 pi. This proportionality constant as a value, and this is the value we have after doing this calculation. So, today I do not have much time. So, today what we learned is very important, that how to tackle with the problem when we try to find out that what should be the total field due to some given arbitrary aperture shape in the case of Fresnel diffraction. As I mentioned, that Fresnel diffraction problem a little bit simple to execute practically, but mathematically its calculation will be a bit tricky compared to the Fraunhofer case. The only reason is that in the Fraunhofer case, the wave front that is coming, they are plane wave, which is easy to deal with, but in this case we have spherical waves where we have additional term 1 by r. So, with that note, I like to conclude here. Thank you very much for your attention, and see you in the next class for more detail about how to calculate the Fresnel's diffraction for a specific case. Thank you.